Hello, everyone. So this is the supplemental lecture talking about the fragmentation of common functional groups. So once again, when we're looking at mass spec, we can actually look at fragmentation of molecules and determine what some of those other peaks are going to look like that are not our molecular ion peak, just based on what stable groups we can form upon fragmentation. And so this is just going through a couple of those very common fragmentation patterns to give you an idea whenever you're looking at some of these mass specs, what you could kind of see. Again, this isn't necessary for solving a mass spec problem, but it can help you out in some situations. So first off, we have alkenes. Alkenes are pretty simple because they fragment to form resonance stabilized carbocations. So you can imagine with this alkene that we have shown over here as our radical cation, if we were to break this bond and give its electrons over to this other carbon, we would essentially form two groups because all fragmentation will form two different things. The first of which is going to be the carbon that the electron was taken away from is going to end up as a cation, and the carbon that the electron was given to is going to end up just as a radical neutral structure. And so for this example, we end up with an M to Z of 41, and this is likely going to be our base peak for this molecule. You can imagine the main reason for this is because we could also draw a resonance form where the electrons from that carbon-carbon double bond could be utilized to essentially form a new pi bond, and we'd have that carbocation in a different place. So that happens a lot of times with alkenes. It just breaks to where we're one carbon away that we can then do resonance with. Alkyl aromatics are very much the same way. They cleave to form resonance-stabilized carbocations, because remember that something like a benzyl cation is very stable, and those will rearrange into what are called tropylium ions. So let's take this alkyl aromatic right here, for example. If this were to fragment where this bond right here breaks, we would end up with what actually is our base peak, because we now have a benzyl carbocation. Right, this is very stabilized by all of the resonance that occurs, even though we do generate an unstable CH3 radical. But all that resonance that occurs can be very beneficial. But the other thing, like I said in this definition, is that we can form what are called tropylium ions. And these tropylium ions, what they are, is essentially a 7-membered ring with a carbocation that is resonance stabilized. So what that would look like here is we could essentially utilize the electrons from this pi bond to form a new carbon-carbon bond with the current positive charge. This then gives us a structure that has a 3-membered ring attached to our 6-membered ring, and we're going to have a carbocation there because we've just lost one of the bonds to that carbon. This can then do a rearrangement where essentially this hydrogen is going to move and do a hydride shift, because at the same time this carbon-carbon bond is going to break and form a new carbon-carbon bond here. Moral of the story here, though, is that we do end up with that tropylium. So once again, a 7-membered ring where we have a carbocation in resonance with all 3 of those pi bonds. And the good news about these tropylium ions is they always show up at a very specific location. If you see an M to Z peak that shows up right at 91, you know that what you're looking at is just a simple substituted alkyl aromatic that upon that cleavage ends up giving you a tropylium ion. Now, when we look at other functional groups, some of the main ones that we're going to care about is those that contain oxygen. So we're looking at alcohols, aldehydes, ketones, all of those. And these can have some slightly different fragmentation patterns, but they still end up doing the same ideas, right? The main thing being we're still forming favorable carbocations. So with alcohols, there are 2 ways that these can actually fragment. The first common one is that of dehydration. What dehydration is exactly what it sounds like. We're losing water. And so this results in a loss of 18 from our molecular ion peak. So take, for example, the molecule up here. We're not going to look at the entire mechanism of dehydration because, to be honest, it is a little difficult and not important for you in this course. But whenever dehydration occurs, we lose H2O. What that ends up looking like for us is that we actually end up with a radical cation species where the location the alcohol was, we end up forming an alkene right beside that. So this would be our radical cation species here, and of course we've lost H2O out the other end. And of course this typically gives us an M to Z value that is exactly 18 below our original. So you can see that our M to Z that we started with, that mass peak, would be right at 88, but upon loss of that group, we end up with a mass of 70. Alpha cleavage, on the other hand, is our other option here, and alpha cleavages are actually very important because this is typically the the base peak of our spectrum, right? Because from our molecular ion, if we get alpha cleavage, we end up with our base peak. So for this molecule in particular, an alpha cleavage is the cleavage of the alpha bond itself. So we can see that this bond that's directly attached to the carbon with the alcohol is going to break, and it's going to give the radical to the carbon that does not have the oxygen attached. Reason being, whenever we lose the electron from that carbon, we end up with a carbocation there. But you can imagine that this carbocation can be stabilized because there's an oxygen right there that can do a resonance donation that gives us a double bond to the oxygen, but more importantly, that'll have filled octets. And so this gives us a mass to charge, in this case, of 45, right? Because we've lost this entire propyl group off the other end. And the reason this is typically the base peak is for exactly what we were talking about, right? Fulfilling octets in a resonance form is much better than leaving something without an octet. So whenever you look at alcohols, you're typically going to see that formation of those carbonyl type compounds. Now, to talk about actual carbonyls, aldehydes and ketones, they operate very similarly to alcohols in some ways. One of those ways being the idea of they also do alpha cleavage. So you can imagine a very similar molecule here, which has an aldehyde. If its alpha bond cleaves, it's going to end up forming this double bond to oxygen. But now we have a carbocation right there. And so this thing is not super stable, but it can still do resonance, right? We still have this oxygen with lone pairs that can donate to now form a triple bond instead of just a double bond like we saw up in the previous example. And so if this actually happens, we end up with an oxygen that's triple bonded to a carbon. And this right here is called an acylium ion. And acylium ions are relatively stable in a mass spec. They're not truly stable outside of it, but it is another very common base peak fragmentation because, once again, having something with octets is better than not. And so you can see for this example, this would give us an M to Z that is 29. So most aldehydes do give you an M to Z of 29 somewhere in the spectrum, although ketones will give you a little bit higher because they'll have carbons attached instead of a hydrogen. Another interesting thing that can occur with carbonyls is something called the McLafferty rearrangement. And so the McLafferty is something that's less common that you may not need to know because the ones above are much more important, but I wanted to bring it up because this does oftentimes give us some interesting peaks. If you have a carbonyl with a long chain, it can rearrange to form an enol. So what this looks like is, unlike with our alpha cleavage, now we're looking not only at the alpha position, but we're looking further to the beta and then the gamma position itself. Because the gamma hydrogen in this case can be essentially taken by the oxygen. This then allows us to use the carbon-hydrogen bond electrons to form a double bond between the gamma and beta positions, as well as then use the beta-alpha cleavage in order to form our double bond that gives us the enol. So after doing this rearrangement, like I had just said, we end up with an enol that looks like this, and it is still a radical cation because all of those electrons are conserved there, and we have our alkene that we made between the gamma and beta carbons shown there. And this, of course, gives us a mass to charge that's a little higher than the typical acylium ion, so right around 44 in this case. So sometimes if you're looking at aldehydes, ketones, all that, and you do not recognize exactly where a specific mass comes in that's not quite the base peak, because that's typically the acylium. It could be the McLafferty that's actually giving you rise to something a little bit heavier. Alkyl halides. We talked about this in the class because we said that we see that halogen mass difference a lot of times that there's halogens present. Alkyl halides typically cleave the carbon-halogen bond. So for example, this alkyl chloride, if we break that carbon-chlorine bond, we end up with a structure that has a carbocation right there alongside a neutral chlorine. And so this gives us a mass to charge in this case of 57, but most importantly, the loss of this here, this is that halogen mass difference. All right, so just keeping that in mind, that is exactly why we see that difference in the spectrum, and it gives us a little bit of visual clarity on where that's coming from. All right, last one, ethers. Ethers are interesting because they take all the weird things about alcohols and carbonyls and it kind of puts them together. First off, we've got alpha cleavage, right? So any of those alpha bonds to the ether can cleave. For example, this one right here can break off, giving a radical to that methyl, as well as a carbocation that is adjacent to the oxygen. And remember that whenever this happens, that oxygen can utilize its electrons to form a double bond, and we have our resonance stabilization. That gives us that right there. This is typically going to be more of our base peak because, again, we have that M to Z that is, in this case, 85, but it's just that fact that we can have something that has full octets rather than having to share them. Another thing that we can do is what's called the carbon-oxygen bond cleavage rearrangement, which is where whenever we cleave the carbon-oxygen bond, we can utilize the electrons from that bond to form an alkene, and then the oxygen can actually end up taking the electrons from a carbon-hydrogen bond that is beta. So what this does is it gives us a fragment in this case that is actually just a radical cationic alcohol. And in this example, it gives us a mass to charge of 58. Right, and so that's alongside this alkene that we generate on the side there. And then lastly, we have the carbon-oxygen bond cleavage. Since oxygen is more electronegative than carbon, it's typically the one that's taking the electrons here. And so that gives us a radical oxygen alongside a cationic carbon. That gives us a little bit lower of a mass. So again, ethers are probably one of the most confusing sets here because it can do so much. But the big picture takeaway of these things is this top route right here, the actual alpha cleavage, this is typically your base peak in the spectrum. So with all those in mind, sort of the key takeaways here is whenever we look at anything with oxygens, alpha cleavage is always going to be viable. Whenever we look at alkyl aromatics or alkenes, we're always trying to form those resonance stabilized carbocations because those are going to be the most favorable things for us. So hopefully that helps a little bit with your common fragmentation patterns, and it should help on the assignments.